This video will discuss the solution to question 23. Consider figure 3. Let L be 1 nanohenry and C be 10 picofarads. What should be the transconductance Gm for the circuit to sustain stable oscillations? And the figure here below is the oscillator that we are going to investigate. It consists of a transconductance amplifier with a gain Gm and a parallel RLC circuit with a resistor, a capacitor and an inductor. To sustain oscillations, the open loop voltage gain of this circuit has to be 1. So, to write that down mathematically, the Barkhausen criterion tells us that the open loop gain has to be 1 with a phase shift of 0. Since the phase shift of the open loop gain has to be 0, we know at least that the frequency of oscillation can be found when the impedance of this RLC circuit has no imaginary component. In other words, the impedance of this capacitor and this inductor completely counteract each other and can therefore be cancelled in this drawing. We can now look at the open loop voltage gain of the circuit. We can call the voltage at this specific node Vx and then look at what happens when it passes into this transconductance amplifier. The transconductance amplifier gives us an output current that is Gm times the voltage difference between the two terminals, which is Vx minus 0, or in other words, Gm Vx. The new voltage at this node can be obtained by multiplying this output current by the equivalent output resistance of the same node. However, the equivalent output resistance of the node is not the same as just this load resistance. The reason for this is that it's been given in the caption that this transconductance amplifier has a finite input resistance and a finite output resistance, and they've not been drawn in the figure. And these are located at the input and output terminals over here, so they are basically hidden components that are right over here. So one here and one over there. So if we want to get the equivalent resistance at this node, we actually have to take all of these in parallel. So it's R in parallel with R in parallel with R out. And that will give us 5 kilo ohms. R is 10 kilo ohms and both of the input and output resistances are 20 kilo ohms, so we get this value. Now we just have to look at the loop gain. The loop gain tells us that we should get the same voltage as a result of injecting the current into this equivalent load as the voltage that we got. That's implicitly what having a loop gain of 1 actually means. So Vx should be the same as the current that we inject times the equivalent resistance, and that is equal to 5 kilo ohms times Gm Vx. We can now cancel Vx on both sides of the equation, and that gives us that 1 has to be equal to 5 kilo ohms times Gm. We can now invert this side to get that Gm has to be equal to 0.2 millisiemens. And that's the correct answer.